Bristol Community College, Mathematics with Dan Avedikian, Math 131, Elements of College Mathematics, Section 3.2, Problem 7. This is Section 3.2, Problem number 7. It says, maximize z equals 15x plus 20y, subject to 2x plus 2y is less than or equal to 3,000, 6x plus 2y is less than or equal to 7,200, 4x plus 8y is less than or equal to 10,000, and x is greater than or equal to 0, and y is greater than or equal to 0. This is a fairly big problem for two reasons. It has an extra constraint compared to most of the other ones in this homework section, and the numbers are fairly big. But it's going to be the same process, that same four-step process, where we're going to draw our feasible region, label the corner points, set up that chart, and then state our solution. So let's start with graph the feasible region. So first of all, what we want to do is for each constraint, each item with a less than or equal to, or an inequality in general, we want to pretend that it's an equation and find 2 points that would make it true when we pretend it's an equation. So the first one on top with the 3,000, I'm going to pretend I have 2x plus 2y equals 3,000, and I'm going to make a little chart next to it with an x column and a y column. And I'm going to color code this again just to make the graph a little bit more clear. So first, let me assume that the value of x is 0, and I have an equation. So if x is 0, I'm left with the equation 2y equals 3,000. So the value of y that would make 3,000 equals 3,000 is 1,500. And now to pick up a second point, I'll do the same process except 0 at the y. And if I 0 the y and I pretend that I have an equation, what I'm left with is 2x equals 3,000. So again, if x is 1,500, 2 times 1,500 would make the equation true. 3,000 equals 3,000. So if x is 1,500 and y is 0, that's another point that makes it true. Now, usually at this point, I start actually plotting these on the graph and drawing the lines. I'm going to hold off just because the numbers are so big. One at a time is not a feasible scale for my graph. So let's see how big the numbers get. Then I'm going to choose a scale based on how big they get. So now the next constraint down has the 7,200 at the end. I'm going to do this one in a different color. I'm going to go to blue. So I'm going to set up that little chart with an x column and a y column next to the inequality with the 7,200. Again, pretend it's equal 7,200 and find 2 points that would make that equation true. So I'll start by letting x equal 0. So if I zero out the x, the equation becomes 2y equals 7,200. So if we divide out the 2, a value of y of 3,600 would make the equation true. So if x is 0, y is 3,600, the equation would be true. And then to pick up a second point, let me 0 the y. The equation that I would be dealing with would be 6x equals 7,200. Divide away the 6 and you'd have 1,200. So if x is 1,200 and y is 0, it would make the equation true. Again, you're just pretending it's an equation. So now I have one last constraint that I have to make a little xy chart next to, the one with the 10,000 at the end. And now I'm going to do that one in a different color still. I'm going to go to green. So now I'm going to let x equal 0. And again, I'm starting with the constraint 4x plus 8y is less than or equal to 10,000. I'm going to pretend this 4x plus 8y equals 10,000. And then if I 0 out the x, it really becomes 8y equals 10,000. That's what I pretend I have. If I divide out the 8, the answer I get is y is 1,250. So if x is 0, y is 1,250 would make the equation true. And one more point. If y is 0, I would have the equation 4x equals 10,000. So divide away the 4 and you'd get 2,500. And now the last two constraints or inequalities, x is greater than or equal to 0, y is greater than or equal to 0, don't produce a lot of extra work. They just lock your graph into the upper right-hand corner of the graph. So I'm not going to make a little chart for those. So now, as I look at the numbers that I have to deal with, the biggest y value is 3,600. The biggest x value is 2,500. I certainly don't want to make 3,600 little lines. So you have to pick a different number scale. So you can pick whatever you want as long as you label it clearly. And the x and y don't necessarily have to run on the same interval. The x's could go 1 at a time, and the y's could go 10 at a time or 50 at a time. For this particular graph, running both x and y at an interval of 500 would work pretty well. So to hit the biggest y value of 3,600 at 500 at a time, if I go up 8 lines, that would get me to 4,000, which is OK. And the biggest x of 2,500, at going 500 at a time, I'd only have to do 5 lines. So 500 is good. Like, you might not necessarily choose the same interval. As long as you label it, it's OK. So I have the graph I started here. So I'm going to label it at intervals of 500. So the x will go 500, 1,000, 1,500, 2,000, 2,500, 3,000, 3,500. That's really big enough at this point, but it doesn't cost me anything. I'll put a few more in. I'll go up to 5,000. And the same interval will work for the y. 500, 1,000, 1,500, 2,000, 2,500, 3,000, 3,500, 4,000. Now that's actually big enough. My biggest y value I have to deal with is 3,600, but I'll put in 2 more. Just again, it doesn't cost me a penny, so the x and the y will both go up by 10 lines. Now what I'll do is actually graph these, fill in the shading and see what the graph looks like. Again, I'm working towards step 1 of graph the feasible region. So for the first constraint with the 3,000 at the end that I started in red, one of the points I have to plot is over 0 up 1,500. That would be over 0 up 1,500. So I'll make a mark for that on my graph. And the other point I have to put on the graph is over 1,500 up 0. So over 1,500 up 0. I'll mark that point on my graph. I'll connect those two with a straight line. There's my ruler. And I must shade either above the line or below the line. So as usual, to determine which side of the line you shade, you want to pick a test point that's not on the line. Use 0, 0 if you can. And 0, 0 is not on the line. I can use it. If I put in 0 for x, 0 for y, I have the statement 0 is smaller than 3,000, which is true. 0 is smaller than 3,000. So my test point came from the underneath side of the line, gave me a true result, so it's the underneath side that is shaded, the side that the test point came from. So. And I won't shade too much because there are a lot of other lines I have to draw on the graph. So the next constraint down with the 7,200 at the end, I started to do in blue. So I'll continue this one in blue. So one of the points that I have to plot is 0, 3,600. So I'll go over 0, up 3,600. Now I don't have exactly 3,600 on my number scale. So by eye, I'll come close to 3,500 is fairly close, and I'll go a little past that 3,500, and I'll plot the first point of over 0, up 3,600. The other point is 1,200, 0, over 1,200, up 0. Now again, I do not have the point 1,200 on my number scale. It goes from 1,000 to 1,500. So by eye, 1,250 would be right in the center, so 1,200 would be very close to the center, maybe slightly before it. Now I'll connect my 2 blue dots with a straight line. Again, I have to decide which side of that line needs to be shaded, above or below. Same process. I'll use the test point that I like to use the most, 0, 0, because it's not on my line. I get to use it. If I put in a 0 for x, 0 for y, I have the result 0 is less than 7,200. Again, certainly a true statement. So my test point came from the underneath side of the line. The result it got when I put it in was true, so the test point's in the shaded side. The underneath side is the shaded side. So I'm not even going to shade above the red line on my graph because I know I have to satisfy all the constraints simultaneously. So I'm just going to shade only the part that's below the red line anyway for the underneath side. Now, the next constraint down that I had started in green with the 10,000 at the end, I have 2 points for that. Over 0, up 1,250. So like some of the others, I do not have 1,250 on my number scale. The Y scale goes from 1,000 up to 1,500. But the 1,250 should be exactly in between. So just by eye, go as close to the center as is reasonable. You don't have to be super fussy. And the other point for the line I'm doing in green is over 2,500 up 0. So 2,500 I have exactly. So the green dot would go over 2,500 up 0. So now I'll connect the two green dots with a green line. And now I have to decide which side of the green line gets shaded. I can either shade above the line or below the line. Same process as the others. I can use my test point that I like, 0, 0, because it's not on the line. Plug in a 0 for x, 0 for y, the coordinates of my test point, and see if the result is true or false. So in the last constraint with the 10,000, I would have the result 0 is less than 10,000, which is certainly a true statement. So my test point came from the underneath side of the line. The result I got when I put it into my constraint is true, so the test point's in the shaded side, so the underneath side is shaded. So again, all of the underneath is shaded for the green line, but because I'm drawing it together with some other lines, I'm only going to shade up to where the red line goes through it, because I can't be out here anyway. I have to be under the red line, under the blue line, under the green line, all at the same time. And now the last two constraints with the x greater than or equal to 0, y greater than or equal to 0, do the same thing as usual. What's going to happen is the x greater than or equal to 0 forces the feasible region to stay to the right side of the y-axis. I cannot use any points that have a negative x coordinate, so I can't get to the left of the y-axis. It has to be only positive x values. And the y greater than or equal to 0 forces me to stay above the x-axis for my feasible region. I have to have only points with a positive y coordinate, so I can't go below the x-axis. So now what I have is an area of overlapping shading that satisfies all of the constraints simultaneously, and this is my feasible region. What I'm going to do is I'm going to darken up the shading. To be extra clear, I'm even going to crisscross it. So that's step one, graph the feasible region, and there it is. Notice I do not get into some of the little triangles formed by the intersection of the different lines. I have to shade the area that is where all the shading overlaps simultaneously. So step two of this process is label the corner points. Now, some of those corner points we pick up very easily because they happen right along the x-axis and y-axis, but there's a couple out in the middle that are going to be more work. So first of all, notice one point we used to make our graph is over 0 up 3,600. That's not a corner point. It does not touch the feasible region. The next one down, over 0 up 1,500, also not part of the feasible region. It doesn't touch the feasible region, not a corner point. This point for the green line is over 0 up 1,250. That is a corner point. So I'll label it. Coming around the bottom, the next corner point I hit is 0, 0. Again, cannot possibly be the maximum, but it is a corner point for our feasible region, so I will label it. Now the next corner point The blue line here crosses the x-axis at over 1200 up 0. So I will label that. Over 1200 up 0. The next one going along the x-axis, the red dot, is not a corner point, doesn't touch the feasible region. Same thing for the green dot at over 2500 up 0. But there are two more corner points that are out in the middle. Where the red line and the green line intersect forms a corner point, and where the red line and the blue line intersects forms a corner point. Notice where the blue line and the green line intersect is not a corner point. It doesn't touch the feasible region. I don't need to find the coordinates of that point. These two I need to find, and where this graph has such big numbers, again, it's not really feasible to try and read it off the graph. You have to solve the equation simultaneously. So you can do them in either order, doesn't matter. I'll start with the corner point where the green line and the red line intersect with each other and find the x and y values for that. So the red line, which is part of that intersection, is 2x plus 2y. I'm going to treat it as equals 3,000. So 2x plus 2y equals 3,000. I don't need the inequality at this point. Now the green line is part of that intersection. The green one is 4x plus 8y equals 10,000. Again, I'm ignoring the less than or equal to. I'm making it an equal to. Now what I want to do for that is either make negative 4x and positive 4x and cancel the x's, or negative 8y and positive 8y and cancel the y's. They'll both give me the same answer in the end. You can choose whichever is easier. The x's seem a little easier to cancel. So what I will do is keep the top, well, I'll keep the bottom. I'm going to multiply the top equation, not times 2, but times negative 2. So negative 2 times 2x is negative 4x. Negative 2 times 2y is negative 4y. Don't forget you have to do this also. Negative 2 times 3,000 is negative 6,000. Not just 6,000, negative 6,000. And now the bottom equation is good the way it is. Just keep it. 4x plus 8y equals 10,000. Now, if I combine the equations, negative 4x, positive 4x, the x's cancel. Negative 4y, positive 8y will give me a positive 4y. And then negative 6,000, positive 10,000 will give me a positive 4,000. So now if 4y equals 4,000, I can divide out the 4 and see that y is 1,000. So the point where the red line and green line intersect has a y coordinate of 1,000. But I still have to find the x. So you can take that 1,000 answer for y and plug it back into either of the original equations to find x. Now again, I think the top equation is a little bit easier. The numbers are a little smaller, so I'll choose the top for that reason. But you should get the same answer from either the top equation or the bottom equation. If I use the top equation and say that y is 1,000, 2 times 1,000 is 2,000. Let me just bring it right down here. So I'm going to have 2x plus 2 times 1,000 equals 3,000. 2 times 1,000 is 2,000. So 2x plus 2,000 equals 3,000. Now, bring the 2,000 to the right side. I'll have 2x equals 1,000. Divide the 2, and x is 500. So the x coordinate of the point where the red line and green line intersect is 500. Now, looking at my graph, over 500 and up 1,000 seems to be pretty reasonable. So I feel that that is the right answer, most likely. Now, next one, I want to find where the blue line and the red line intersect with each other. So let's find which equations we would be working with. The blue line is the one that ends in 7,200. So let me just write the equation. 6x plus 2y equals 7,200. So that's the equation for the blue line. And again, I've left out the less than or equal to. I just want it equals. And now the red line is also intersecting to find that corner point. That's the equation with the 3,000. So written as an equation, the red line would be 2x plus 2y equals 3,000. Again, forget the less than. So what I would like to do is cancel one of the variables, and I can cancel either one. The y seems lined up a little nicer. So let me bring it down underneath. The top one can stay as it is. 6x plus 2y equals 7,200. Now the bottom one, I'd like to make the 2y that I have negative 2y. So for the bottom equation, everything's going to get multiplied times minus 1. Minus 1 times 2x is negative 2x. Minus 1 times 2y is negative 2y. And minus 1 times 3,000 is negative 3,000. Now when I combine my two equations, positive 6x, negative 2x is positive 4x. Then positive 2y, negative 2y will cancel, which is great. Positive 7,200 and negative 3,000 would be positive 4,200. Now, to solve for x, I'll divide away the 4. X is 1,050. So the point at which the red line and blue line intersect with each other has an x-coordinate of 1,050. Now, I need to find the y-coordinate. And I can take that x is 1,500 and put it into either of the original equations. The one with the 2x, 2y seems a little bit easier because I just have a little smaller numbers. So let me use that one. So now the 2x, I'll write over here, becomes 2 times x becomes 2 times 1,500. Then plus 2y equals 3,000. So 2 times 1,500 is 2,100, plus 2y equals 3,000. So now bring the 2,100 to the right side of the equation, and you'll have 2y equals 900, right? 3,000 minus 2,100 is 900. Divide away the 2, and 2y equals 900, and you'll have y equals 450. So the y-coordinate, according to my computation, is 450. So again, looking at my graph, my 1,050 for my x-coordinate seems reasonable. It's a tiny bit past the 1,000, which seems good. The y-coordinate, a height of 450, seems reasonable also. It's a tiny bit below the 500. So now, step 1, graph my feasible region. I drew the graph. Step 2, label the corner points. I did that. That was a good amount of work. Big numbers again. Step 3, fill out the chart. So I'm going to make a chart that's going to list my corner points, have my object function in the middle, and do the outputs. I should have enough room to do it underneath the problem. So the far left column I typically label corner or corner point. The middle column, which I make wider, I use for my object function, which for this particular problem is z equals 15x plus 20y. And last column is output. So now I have 1, 2, 3, 4, 5 corner points. So I'll make 5 rows for my chart. You can list the corner points in any order. I'll start with 0, 12, 50 and work my way right around. So one corner point is 0, 12, 50. The next one going around my feasible region is 500, 1,000. The next corner point I'll put in my chart is 1,050, 450. The next one is 1200, comma 0. And the last one is 0, 0. Again, I know 0, 0 can't possibly be the maximum, but I'll put it in my chart. So start plugging them in. So the first corner point, 0, 1250, means you have an x value of 0 and a y value of 1250. Plug that into your object function. So 15 times x will be 15 times 0, and 20 times y will be 20 times 1,250. 15 times 0 is 0. 20 times 1,250 will be 25,000. And then when you add 0 plus 25,000, the result is 25,000. The next corner point down, 500 for x and 1,000 for y. The 15 times x is 15 times 500. And 20 times y is 20 times 1,000. So 15 times 500 is 7,500. Now these seem like very big numbers. I'm essentially just doing 15 times 5. And I know that's 75, and I put the 2 zeros back. Feel free to do stuff like that with your calculator. And the next multiplication, 20 times 1,000, is 20,000. And now 7,500 plus 20,000 is 27,500. So our output has gotten a little bigger. The next corner point down, 1,050 for x and 450 for y. So 15 times x becomes 15 times 1,050. And then 20 times y becomes 20 times 450. So 15 times 1,050, you're going to have 15,750. And then 20,000 times 450 is 9,000. And then 15,750 plus 9,000 is 24,750. And the next corner point down, x is 12,000, y is 0. So 15 times x is 15 times 12,000. 1,200, sorry, 15 times 1,200. And then 20 times y is 20 times 0. So 15 times 1,200 is, let's see, it's 18,000. And then 20 times 0 is 0. 18,000 plus 0 is 18,000. And then finally 0, 0. 0 for x, 0 for y. So I know that's 0. So 15 times x is 15 times 0. 20 times y is 20 times 0. They're both 0. You add 0 plus 0, you get 0. So now, this problem said maximize. So to find the maximum, we have to choose from the following outputs: 25,000, 27,500, 24,750, 18,000, or 0. So there's certainly big numbers, but clearly the biggest possible output is the 27,500. So the last part of this process, which says state your solution, I'll put it right here, we'll say maximum of 27,500 at the point So where did that 27,500 come from? It came from the point 500, 1,000. So if I go over 500 up 1,000, that's the point that gives me the maximum output. So over 500 up 1,000. So for this problem, the maximum possible output is 27,500, which comes from the point with an x coordinate of 500 and a y coordinate of 1,000.